Imagine you are sitting on a high-speed train, gliding effortlessly at 155 miles per hour. Everything feels normal until you realize that you are currently 256 feet below the ocean floor. That is roughly the equivalent of a 25-story building buried deep beneath the earth. Above your head, massive cargo ships are traversing one of the busiest shipping lanes on the planet, completely unaware of your presence. At this extreme depth, the sheer weight of the ocean creates a water pressure so intense it could crush a standard vehicle like a discarded soda can. Yet, there you are, perhaps scrolling through your phone or enjoying a light snack, entirely unbothered by the millions of tons of salt water overhead. It sounds like a scene from a high-budget science fiction movie where humanity has finally mastered the impossible, but this is the reality unfolding right now in China. They are constructing an undersea tunnel so technically extreme that when it officially opens in 2028, it will shatter every existing record for underwater rail construction. It is currently May 2026, and as we look at the progress of global infrastructure, the Gintang undersea tunnel stands out as a titan of engineering. This project spans over 10 miles in total, with nearly 7 miles of that distance carved directly beneath the seabed of the East China Sea. To give you a better perspective on that scale, it is longer than the daily commute for many Americans, except this particular journey involves two colossal tunnel boring machines the size of apartment complexes, meeting deep underground with the precision of a surgical instrument. We are witnessing a moment where the boundaries of civil engineering are being pushed to their absolute limits. The sheer speed and scale at which this project is moving make previous underwater efforts look like mere practice runs. Today, we are taking a deep dive into how this feat was pulled off and why it represents a significant shift in the technological balance between East and West. The motivation behind such a massive undertaking is purely strategic and economic. Zhoushan is a cluster of islands off the eastern coast of China, known for its fishing heritage but more importantly as one of the largest offshore petrochemical bases in the region. Despite its industrial importance, it had zero railway connections to the mainland. For years, the only way to move people and goods was by ferry or a series of bridges. While bridges are impressive structures, they have their limitations, they occupy surface space, are vulnerable to extreme weather, and can obstruct the very shipping lanes that fuel the economy. Tunnels, however, are the ultimate solution for seamless connectivity. They remain unaffected by surface storms, waves, or the massive tankers passing above. Over the last decade, China has built over 28,000 miles of high-speed rail, which is more than the rest of the world combined. They have mastered the mountains and the plains, and now they have taken on the final boss of infrastructure, the deep ocean. This is not just a tunnel for commuters. It is a high-speed artery designed for trains traveling at speeds that exceed most cars on a highway, functioning in one of the most geologically complex environments imaginable. To understand how a project of this magnitude is even possible, we must look at the stars of the show, the tunnel boring machines. These are not your typical construction vehicles, they are absolute mechanical monsters. The two machines specifically engineered for the Gintang tunnel are named Dinghai and Yongzhou. Each one measures approximately 492 feet in length. To put that in perspective, if you stood one of these machines on its end, it would reach nearly half the height of the Eiffel Tower. The cutter head alone, the massive spinning disc at the front that actually grinds through the earth, is nearly 49 feet in diameter. Imagine a circular saw the size of a 5-story building, spinning with enough torque to slice through solid granite as if it were soft butter. Each of these machines weighs around 4,000 tons, roughly the equivalent of 8 fully loaded Boeing 747 jets. They are fully automated engineering marvels that represent the pinnacle of modern heavy machinery. As the cutter head grinds forward, the machine performs several complex tasks simultaneously. It removes debris, installs reinforced concrete rings to support the tunnel walls, and injects grout to seal everything in place, preventing the ocean from seeping in. It is essentially like building a high-tech skyscraper horizontally underground in real time. However, the most difficult part of this journey is the unpredictable nature of the ground itself. Engineers call this mixed geology. Along the tunnel route, the conditions change constantly. One moment, the machines are boring through solid granite, hard, stable, and predictable. The next moment, they hit soft clay or sandy soil that can shift or collapse if the pressure is not managed perfectly. Over the course of the 11-mile underwater stretch, these machines encounter 28 different geological transitions. This means 28 times the operators must adjust speed, pressure, and cutting techniques to avoid a catastrophic failure that could flood the entire project. To handle these brutal conditions, the engineers implemented several custom modifications that highlight the current gap in rapid infrastructure deployment. They added specialized water injection systems to the cutter head to prevent sticky clay from clogging the blades, which is a common problem that can stall projects for months. They also reinforced the sealing systems to withstand the crushing hydraulic pressure at 256 feet below sea level. The drive systems were upgraded to ensure these machines could operate non-stop for months without a single mechanical breakdown. The logistics are mind-boggling. One machine, Yangzhou, started digging from the Ningbo side on the mainland, traveling nearly 3 miles. The other, Dinghai, started from the Zhoushan Island side, covering over 3.7 miles. Somewhere in the middle, deep beneath the churning waves of the ocean, they were destined to meet. But in the world of engineering, you cannot just eyeball a project like this and hope for the best. If these two machines missed each other by even a few feet, the result would be the most expensive failure in history. The challenge of connecting two massive machines deep underground is often compared to threading a needle, but the reality is far more complex. Imagine trying to thread that needle when the eye is 50 feet wide, buried over 250 feet below the ocean floor, and you are guiding the thread from nearly 4 miles away. Even a tiny error in the starting angle, as small as a single degree, would result in the machines being dozens of feet off target by the time they reach the middle. In the harsh environment beneath the seabed, traditional measurement tools are useless. To solve this, the project turned to a sophisticated satellite network that rivals our own GPS. By deploying 6 Beidou satellites specifically for this mission, engineers were able to link the machines to a high-precision positioning system that tracks every movement in 3-dimensional space. These satellites monitor latitude, longitude, and depth, allowing for micro-adjustments in real time. If a machine drifts even a fraction of an inch off course, the system automatically corrects the steering. This level of precision is what sets modern mega-projects apart. Every few feet, the machines send signals to the satellite constellation, which calculates their exact coordinates and compares them to the digital blueprints. Think of it as a GPS accurate to within less than an inch, guiding a 4,000-ton titanium beast through solid rock. When Dinghai and Yangzhou finally met deep under the East China Sea, the alignment error was found to be less than 0.8 inches. To achieve that level of accuracy over a distance of nearly 7 miles is the equivalent of a professional quarterback throwing a football from one end of a stadium and hitting a target the size of a coin at the other end. This success demonstrates a mastery of automated navigation that has significant implications for future infrastructure projects globally. It proves that with the right combination of satellite technology and automated machinery, the physical barriers of the ocean floor are becoming increasingly manageable. However, completing the tunnel creates a final, unusual problem. Once these two machines meet face to face, they have nowhere left to go. They are far too massive to be put in reverse and backed out through the miles of tunnel they just created, and there is no exit path ahead of them. This leads to a fascinating process known as shedding the shell. Engineers enter the tunnel and carefully dismantle the machines from the inside out, piece by piece. All the high-value components, the drive systems, the hydraulic pumps, and the expensive electronics are salvaged and hauled back to the surface. But the outer steel casing, The massive cylindrical shield that protected the internal workings is left behind. It is permanently fused into the tunnel structure, serving as an extra layer of reinforcement for the walls. It is a poetic end for these giants. They do not just build the path, they literally become part of the foundation that will support high-speed trains for the next century. As we look at these incredible engineering achievements, it raises some interesting questions about the future of how we connect our world. When we see such precision and scale being achieved under the most difficult conditions, it makes us wonder what the next frontier will be. Do you think the benefits of these multi-billion-dollar undersea links outweigh the immense technical and environmental risks involved? How do you feel about the transition from traditional bridges to these hidden, high-speed underground corridors? I would love to hear your thoughts on this, so please share your perspective in the comments below. Beyond the immediate benefits of connecting Ningbo and Zhoushan, we have to look at the broader strategic implications of the Gintang undersea tunnel. While the project is a marvel of civil engineering, many international analysts and experts believe it serves a much larger purpose than just local transportation. In the world of high-stakes infrastructure, a project like this is often a proof of concept or a massive testing ground for even more ambitious goals. The technical data gathered here, how the boring machines handle extreme pressure, how the satellite navigation performs miles underground, and how the concrete holds up against the corrosive nature of salt water is being meticulously documented. This is essentially a laboratory for the ultimate engineering challenge, a potential tunnel across the Taiwan Strait. When we look at the maps, the distance between mainland China and Taiwan at its narrowest point is approximately 81 miles. That is roughly 8 times the length of the Gintang tunnel. The water is deeper, the currents are significantly more treacherous, and the geological fault lines make it one of the most difficult places on Earth to build anything, let alone a high-speed rail link. If any nation intends to attempt a feat that has been considered impossible for decades, they do not simply start on day one with the final product. They build smaller, yet still incredibly challenging, versions to refine their techniques. They develop the specialized machines, they train the elite teams of engineers, and they lower the costs through repetition and innovation. By completing the Gintang project, a clear message is being sent to the global engineering community. The ability to build high-speed rail under the ocean at depths that would crush conventional structures with precision measured in fractions of an inch is no longer a theory. It is a proven capability. For decades, underwater tunnels were considered the final frontier of civil engineering, projects so expensive and dangerous that most nations might only attempt one or two in their entire history. In contrast, we are seeing a pace of construction that treats these mega projects as if they were routine infrastructure updates. The Hong Kong-Zhuhai-Macau Bridge, which features a 4-mile underwater section, was just the beginning. Gintang is the next step, and the scale is only going to increase from here. From an American perspective, we often view infrastructure through the lens of cost-benefit analysis and environmental impact studies that can take years, if not decades, to conclude. This leads to a very different pace of development. The ability to centralize resources and move directly from a blueprint to a finished undersea tunnel in such a short time frame is a testament to a different model of industrial planning. However, this speed also brings up significant questions about long-term sustainability and the environmental toll on marine ecosystems. Drilling through the seabed on such a massive scale inevitably disturbs delicate underwater habitats, and the long-term effects of high-speed vibration and electromagnetic fields on local sea life are still being studied. Furthermore, the sheer financial investment required for these titans of the sea is staggering. We are talking about billions of dollars being poured into a single tunnel. While this drives economic growth and creates thousands of high-tech jobs, it also places a heavy bet on the idea that physical connectivity will remain the primary driver of the economy in an increasingly digital world. As these tunnels become more common, the very definition of what is impossible in engineering is being rewritten before our eyes. As we look at the completion of the Gintang undersea tunnel, which is on track to be fully bored through by the end of this year, we must consider what it means for the world when one nation fundamentally redefines the limits of possibility. 50 years ago, the idea of a high-speed train traveling at 155 miles per hour through a tunnel 256 feet below the ocean would have been dismissed as pure fantasy. Even 20 years ago, while theoretically possible, it would have been seen as an economic and technical nightmare that no sane government would approve. Today, it is a reality that we are watching unfold in real time. This shift in the global infrastructure mindset is profound because when one country demonstrates that a project of this scale can be done efficiently and safely, it forces every other nation to reconsider their own limits. Suddenly, projects that were once deemed too risky or too expensive for the United States or Europe are being looked at with fresh eyes. The techniques pioneered here, from the automated navigation to the innovative shedding the shell method, are likely to become the new global standards for civil engineering in the coming decades. However, we must also address the complexities and the hidden costs that come with such aggressive progress. These mega projects do not exist in a vacuum. There are legitimate concerns regarding the environmental footprint left on our oceans. When you drill through miles of seabed, you are not just moving rock. You are disrupting ancient ecosystems and altering local marine biology in ways we may not fully understand for another 50 years. There is also the social and economic dimension to consider. These tunnels represent an investment of billions of dollars, a sum that most countries simply cannot afford to gamble. This level of spending is driven by a centralized planning model that prioritizes national infrastructure as a primary engine for economic growth. Whether this model is truly sustainable over the long term, or if it will lead to a surplus of expensive infrastructure that the future economy might not fully utilize, is a question that economists and political scientists will be debating for a very long time. It is a high-stakes game of building for a future that is still being written. Ultimately, the Gintang Undersea Tunnel is more than just a shortcut between a mainland city and an island chain. It is a symbol of a new era. It is an era where the barriers between landmasses are being dissolved by technology and where the depths of the ocean are becoming as accessible as the mountain passes of the past. As we move closer to the official opening in 2028, the world will be watching closely to see if the reality lives up to the monumental engineering promises. It serves as a reminder that the race for technological or engineering supremacy is not just about who has the fastest computer or the most advanced satellites, but also about who can reshape the physical world to meet the demands of the next century. The rules of what can be built and how fast it can be completed are being rewritten, and the implications will be felt in every corner of the globe as we decide how to connect our own communities. As we close this analysis, I want to leave you with a few final thoughts to consider. If you had the power to authorize a multi-billion-dollar undersea tunnel anywhere in the world to connect two regions, where would you choose to build it and why? Do you believe that the drive for such massive physical connectivity is still the most important goal for a modern nation? Or should our resources be shifted elsewhere? These are the questions that will define the next generation of global development. I am very interested to see your perspectives on this, so please take a moment to share your thoughts and join the conversation in the comments below. Thank you for joining me for this deep dive into the future of engineering.